Hello, everyone, and welcome to the Ask the Expert webinar, Explainable AI, Techniques and Tricks to Improve the Interpretability of Machine Learning Models. My name is Thiago de Souza, and I will serve as your moderator for today's event. Now, I would like to take a moment to introduce our presenter, José Belo Aragão, Jr. From Farias Brito University. He is a professor, a data scientist with solid experience working on machine learning, statistical simulation, and data engineering projects using the SAS platform, including SAS Via. José, please take it away.
Thank you, Thiago. Okay, I'm José, and I will introduce to you this very important area. This is the explainable AI. Then I will start talking about the selection of machine learning algorithm. When we start our projects in machine learning, we need to focus in this choice. Okay, what kinds of algorithms we need to use? If you are interested in accuracy, we need to use very strong algorithms like neural networks or gradient boost or forest. We know that these algorithms are very powerful. They use very strong techniques, but on the other hand, these algorithms suffer with low interpretability. In the most of the case, we can't explain how one result was made by these kinds of algorithms. In the other side, in the right side, we have some algorithms like decision tree or logistic regression. These kinds of algorithms are very they have high interpretability. For example, with decision tree, we can just follow the rules created by the tree and explain why a decision was taken. Then this is our focus here is to try give to these algorithms like neural network a way to understand their results. Let me pass to the next slide, just a moment. Okay. These kinds of algorithms like neural network are nodes like black box algorithm. Then what is this concept? What is a black box? Okay, the black box, it's when we just present to algorithm some inputs, and then we collect the output, but we don't know what is happening. For example, with in machine learning, what is happening in which layer, for example. Then our mission here is open this box and try to understand what is happening here when we introduce the inputs and then collect the response of the model. Then this is the mission, the goal of the explainable techniques AI. Okay, it's a set of tools, okay, to help us to develop interpretable machine learning models. Then this way we can explain and improve the transparency, trust, and accountability of this is very important, for example, in health, in justice, in finance areas. Okay, in SASVIA, we have two groups of explainable AI techniques. We have the global techniques. In this area, we have the partial dependence plot and variable importance. And in the local group, we have the individual conditional expectation and local interpretable model agnostic explanation. And the SHAP. SHAP is an acronym for Shapley Active Explanation. After this presentation with slides, I will show to you a demo in SASVIA using these techniques. Okay, let's go. The first variable importance, it's very common in SASVIA. With this technique, we can identify the contribution of each variable in the model. This number can be calculated on various ways. For example, here we have the importance calculated by the difference in the function loss. When I remove that variable, then we can see here in this example, for example, this variable, when I remove this variable, the error of the model increase a lot. In some tools in SASVIA, you can see, for example, can see, for example, relative importance. Then relative importance is calculated, for example, in percentage mode, or for example, when we run a decision tree with just one level. And then when I run decision tree with just one level, I can calculate, for example, the gain of information. Okay, how many entropy was decreased with this variable. Okay, this is the award. This is the most important variable. And then we have the next is the partial dependence plot. This is very nice technique, very simple and so beautiful plot. This technique shows the average relationship between one or more inputs and the model output, rounding all the other variables constant. This is very nice. For example, if you see this picture, sorry, you can see here some values, okay, equally spaced. Then what is happening here? After the training of the model, we can, for example, see the results. Okay, we will have a model trained, but for example, I want to see the behavior. If I input this variable, in this case, RFM1, average sales past 3 years. If I input all these runs for these features in this column with this value 10, I will change all the values of this variable with just 10. Okay, then I introduce this new data set for the model trained, and then I collect the response of the model. After this, these results, I calculate average of the response, and then I put here. Okay, this is the average when I when I input all the values of this variable with value 10. And then this process is repeated with other values. And then, sorry, we have the total behavior of the result of the models when this variable is changed. Okay. This is very important. Then we can, for example, choose some variables and then analyze the behavior for changing the value that variable unique or with 2 or 3 variables being analyzing. Okay, the next technique is the ICE individual conditional expectation. NICE, it's very similar to PD. The PD plot is showed here too. In this example, is this blue line. But the difference is because this technique make part of that local group. In this case, we can analyze what is happening in a local instance. In Sasvaya, we can choose five instances, for example, and then analyze what is happening with this local instance. But okay, you are asking why this value is changed if I just have one instance. Why these values are calculated? Okay, in this case, when we chose an instance, we will freeze all the values of other features, other variables, and this variable, for example, in this example, will be changed. Okay, then we will, for example, for this instance, test with 10 and 12 and 14, and calculate the response. This is so nice, but maintain the other values constant for this instance. Then we can analyze the behavior when we change this variable for this instance. This is an ID. This is interesting because if you see after this process, if you see all the lines in a parallel mode, this is good because this show a constants of the model for this variable. But for example, if you see the lines intersecting, this can show to us, for example, a very significant, or even, for example, interaction between two variables. For example, age and income, for example. Okay, then this is the best kind of results with ICE. Okay, let's do the next. The next is the LIME. Okay, LIME. For me, to me, this is the most beautiful algorithm in this area. Local interpretable model agnostic explanation, LIME. In LIME, LIME will create syntactical data uh, in the neighborhood of an instance. Then, for example, here we have a local instance chosen, and then here we have a linear regression. This is very okay. But what is these bars? This bar is represents the value of the coefficients of these others this variable. Then this is a model, a linear regression model in the neighborhood of this instance. Okay, but how this model is generated? This model is generated starting with syntactic data. This syntactic data is created starting off this instance and just perturbing some values of these features that this instance. Then imagine if you have four features, 10 x1, 10 x2, 15 x3, 20. Then I can just input change 10 for 9, change 15 for 16, around that instance, and then generate similar samples. And then I introduce these similar samples to the model, original model, and collect the response. And with this new syntactic data set, I can create a linear regression. In this case, in Lime use lasso penalization to avoid the increase of the coefficients. Okay, and the last algorithm is the SHAP. SHAP, it's acronym for Shapley Additive Explanation. This algorithm comes from the game theory. Shapley values. Shapley earned award. Oh my God, I forgot the name. that award, a Nobel Prize, and now his tool is used to in this area, explainable AI, and then we can let's just a minute, please. SHAP showed to us the contribution of each variable for the result of the model to a local instance. Then, for example, in this example, we have here a local instance, a sample. Then this sample has a result emitted by the model, and then SHAP in the SASR hyperSHAP showed to us the contribution of each variable for that result. Then during this calculus, SHAP will test each variable. Okay, I put this variable. How this value, how much is the difference for the average, the average response? And if I put one more variable, what is happening then? SHAP creates a lot of combinations to give us the final contribution for each variable. This is fantastic. Now, after this, well, I present the idea of this algorithm. Then now I will show to you where I can use this inside SASVIA. Just a minute, I will share my screen. with you. Just a minute. Okay, I think you can see my screen now. Okay, thank you, Chuck. Then I will open a demo that I left created to show to you. Okay, this is a little project that I made. And in this project, I'm using here. I'm in SAS Explore and Visualize. This is SAS Visual Analytics, known now SAS VA. And then I'm using a very famous data set in SAS via environments, VS Bank. This data set is used in, in various trainments from SAS. And here the goal is identify if a client will will buy or contract some product again. Then this is the proportion of in the data set of no if you the amount of uh, buyers people will buy something again, and then this is bad clients. Okay, then here we have a decision tree model. I'm using here just 14 variables. 12 is continuous, and two category, okay, nominals. And this is a decision tree, and then uh, decision tree, it's a very good model if I want to explain what is happening. Okay, in this decision tree, I left just 611, the maximum, and here we have the holes. Then, if I want to track a response, I can I can explain using these rules. It's very good. And here we have a neural network. I just put in this neural network one hidden layer, and here we have uh, some statistics, okay, convergence, confusion matrices, okay, but we can how to explain what is happening, our a predicted number was emitted by the model. But even in these environments, SAS VA, we already have some explainable AI tools like relative importance. I already said to you. Look that the maximum value is 1. Uh, and we have the partial dependence too. Look this. Then, for example, this variable RFM5. Okay, I transform this variable using the log function to avoid the asymmetry. But okay, look, when this variable increase, the predicted probability increase too. It's almost directly relationship. Uh, and the first technique, the other technique that I want to show to you, I like a lot. It's, for example, in this environment, I can derive predicted. With when we do this, look here, we will have, okay, we will have new variable just in metadata, but we can see this. I will put in this table our ID and the original target and the result of the model, probability and the predicted. Okay, apply. Then I have here the original target and the target the response of the model. Okay, and here the probability. But what I want to show to you is how we can explain this neural network, for example, using a decision tree. Then now I will okay, I will do this. I will just duplicate our decision tree. Then I will rename to decision tree to for neural network. Okay. But here I will change the response, our target. I will change this for the target predicted target emitted by neural network. This way we can train a decision tree and we will have rules here that explain what the neural network did. It's better if you ask, for example, a filter. This I will remove here just a minute the partition. I will remove, and I will filter this model. Just a minute. I will filter with just the validation partition. Okay. Then now I can explain the decision taken by the neural network. This is a way to try to explain. Of course, it's a approximation. Then now, okay, I already showed to you this way and these two choose. And now let me save, please. Then now I will show to you the other tools, but the other tools are in the other environment and build models from Model Studio. Just a minute. Okay, I already left a pipeline here in this project. I'm using the same data set, the same variables. You can see here, I left here just in the whole input, just the same variables, but here I did, then I use here just a node to imputation, and I connect a neural network in this node. And here I connect a transformation node, and here I chosen the best way. Then I left Sasvaya chose the best transformation for each variable. Then what? Why you do this, Jose? Well, here, if you see the result of this node, you can see that just one variable was inputted. Okay, and his name is changed. Now I have this prefix EIMP from input. But okay, I know that this variable comes from FM3. I can track, I can understand the source of this new variable. And when I transform to correct uh, uh, some things, bad things in my variable, for example, the result from this node, look this. Oh my God, a lot of transformed variable. Log one inverse of SQRT. Okay, but even this, we can track the original variable, because this is a transformation one by one. Why I'm show this to you? Because when I use this, for example, neural network with one hidden layer 2, and now we have the model interpretability tools in the global group and local group. Global, variable importance and PG plots, and in the local group, ice, lime, and shell. Okay, let's just see this. Okay, this is our neural network diagram, and here the model interpretability tab. Then here we have the partial dependence. It's the same from the older environment. Here we have the ice with partial dependence. Look, this is the local instance chosen by the Sasvaya, because I didn't choose. And what is happened? Here we have the Lime explanation for this local instance. These instances we can choose here. Just a minute, please. Okay, look this, random. Then the two will choose, but we can specify up to until 5. Then return to the results. We have here the lime this is the coefficients. Look, these coefficients. Just these three variable is making part for the linear regression model around this instance. Remember that this technique use lasso, okay? To lasso, it's very, very hard, very good to kill some coefficients with that if this coefficient doesn't importance. And here we have hyper sharp values around this instance. If you see the result of this instance by the model, this is the contribution of each variable for that result. This is fantastic. Look this, the value. Okay. Then, oh my God, I just have 5 minutes. Okay. Then now I will show to you another technique. After this transformation, I put another neural network, and here you can see, for example, we can explain what is happening, but now looking for the new variable transformed. But okay, we still can track the original variables. But here we have another situation. What has happened here? If you use a node like feature extraction, this node use some algorithms like PCA, principal component analysis, and this kind of algorithm, PCA or SVG, for example, or autoencoder, they change totally our feature space. Then now, for example, we will have new variables, and new variables is totally different from the original variable. We lost the possibility of track the original variables. Just a minute. Murphy laws now? No, please. Okay, then this is our new variables. Each variable, it's a linear combination by our original variables. In this case, we have just 10 because of the cumulated variation. It's 10. And this variable will be introduced to neural network. Then if you see the result of this neural network, now we have, oh my God, what is this? We lost the capacity to look to input and the output and understand what is happening, because our inputs are lost when I use that technique, PCA or SVG. Then this isn't important anymore. But SAS Viya gives us another trick, a very good trick. It's a Ansible trick. Ansible, it's a node very good to combine the results of various models. For example, I can connect here a neural network, a decision tree, a forge, a gradient boost, and then combine the results and and obtain a new result. But if you use the Ansible node receiving the output of just one model, like here, uh, an incredible thing happen. Ansible node may make like a bypass around the by the any transformation around the path until him until it. And when we look for its results, look the magic. This is fantastic. Okay. Uh, this node gives us two techniques and three techniques, very important, but okay, it's totally zero or some different from zero. But it's a very uh, small number. But if you see to here the lime and shape, we can see the relationship, or we can analyze what is happening in the local instance. But now looking for the original variable. This is fantastic. This is a great bypass. Then this is possible when you are using the Ansible node with just one model. This is a good trick. Okay, then this is all that I wanted to show to you. I think you are think good, and this. It's with you, Thiago, now.
Thank you. With that, we will be moving into the Q&A segment of the webinar. All right, Jose, now on to our first question here. Someone's asking, what is the difference between individual conditional expectation curve and linear regression curve? Is it the same task of prediction?
No. The ice in the ice plot, we collect just the result just of one instance. Okay, one instance, but I will change the values of just one variable. In the Lime, I will change the values of all the features, but just little changes, like a perturb. And then I will create a linear model, use like a linear regression technique. It's another model. ICE isn't a new model. This is the difference.
Thank you. I'm afraid that's all the time we have. There are some helpful user resources and links here on our final slide. On behalf of myself, Jose, and all of SAS, we really hope that you enjoyed today's webinar. Thank you all, and have a great rest of your day.